Welcome everyone to note video number 4, and in this note video we are going to be discussing the 4 states of matter, well, 4 of the 5 states of matter, and we're also going to talk about what you call it when matter moves from one state to another. So you're very familiar with 3 of the 4 states of matter. You're very familiar with solids, liquids, and gases. So let's hit those ones up first and get them out of the way. So solids look something like this. We have all of the matter and molecules and compounds and atoms that are all nice and tightly fit together. Solids by definition have a definite shape, which means their shape doesn't change on its own, and it has a definite volume, which means, you know, if you have something that is 6 cubic centimeters and you leave the room and come back, it's going to be 6 cubic centimeters. It's not going to change depending on where you put it. There are 2 kinds of solids, though. One is called a crystalline solid, and crystalline solids make up crystals. And crystals are solids that have repeated patterns. You're going to see a picture of it here in a second. But no matter where you look in that crystal, you're going to see the same structures. Atomically, they're going to have the same number of atoms in the same places, and it's just going to be repeated over and over and over again. Good examples of things that are crystalline solids are things like your salt and your sugar. Salt is a very cool crystal to look at because it's perfectly cubic. So some cubes are bigger than others, some cubes are smaller than others, but the angles of the way that the molecules come together and the atoms come together always makes really nice 90-degree triangles. So it makes very square ones. Sugar has a different structure to it. It's not as nice and easily recognizable as a cube. But one thing that all crystals have in common is crystals tend to have really high melting points. So if you wanted to melt salt, for example, boy, do you have to get salt really, really, really hot to melt. I don't remember the actual temperature, but it's something ridiculous, like 700 degrees Celsius. It's outrageous. Sugar melts at a lower boiling point than that, but still has to get things really, really high to melt a crystal. The opposite of a crystalline solid is called an amorphous solid. You may remember from 7th grade some vocab terms that were like a term and then another one with an A in front of it. Well, in English, if you use the prefix a before something, like there's typical things and atypical things, by putting the letter A in front of it, it means the opposite or not. So morphous would be solids that would have a shape, or a structure to them. Amorphous solids are solids that don't really have a pattern structure. So these are things like plastic and rubber and glass. One of the most important differences between crystalline solids and amorphous solids is since crystalline solids have this repeated structure to it, they tend to shatter if you try to flex them. They're very rigid but brittle, and they'll actually break along these lines of atoms. It's what jewelers take advantage of when they do things like cut diamonds. They cut the diamond right along the edge of all of the carbon atoms that happen to be in a diamond, on these really nice smooth planes. You can't do that with an amorphous solid because amorphous solids have like a hodgepodge of connections going on. But it also does tend to make them more flexible. That's why rubber and plastic things, you can bend them a little bit easier. You can't bend a salt crystal at all. Liquids are the next state of matter that we'll talk about here. And liquids are a fluid, and something is called a fluid when it can flow. And the reason that a liquid can flow has to do with the structure and the molecules and the atoms. So liquids have a definite volume, but not a definite shape. So if you have a liter of water, you're always going to have a liter of water no matter what material you pour it into. One of the things that's really important about liquids is you can't compress them. You can't squeeze a liquid. And it's how we can run really big machines on hydraulics. It's also how you can stop your car. It also works with hydraulics. So the way that it works to stop your car is you have a line of brake fluid that goes essentially from the pedal to the discs on the tires. And when you push on the brake pedal, you push on that fluid, but since fluid can't be compressed, the force that you push down on the brake is directly channeled to the little pads on the tires. You're not losing any power along the way. But it's also dangerous if you get an air bubble in your brake line and you push on the brakes. Instead of it being like a nice solid connection of liquid that goes down, if there's an air bubble in there, you can compress air. You can squeeze air down into a tinier amount of space, a tinier volume, and you wouldn't be able to stop your car nearly as well. The reason that fluids can flow is because the actual positioning of the molecules and atoms that are in here, they are still touching each other like they are in a solid, so all of the molecules are in contact with other ones, but they have the ability to kind of roll and tumble over top of each other. And since they can slide past each other, that allows fluids to have this property where they can flow. One interesting thing about liquids to take note of is called surface tension. In surface tension, this occurs where the liquid touches the air, so at the surface. But what happens is that the molecules that are up there get like a really strong attraction to all the ones next to them, and it kind of creates this force barrier at the top of the material. It says that it's kind of like a tough skin, but it's not something that's physical. It's like an energy. It's like an attraction that holds all those molecules in tighter placement. So some animals have evolved to really exploit this. Things like bugs that can crawl around on the water. So if you look, this bug is actually standing right on the water. It's not heavy enough to break through the surface tension. So it is not pushing with enough force to separate those molecules on the surface of the water, and it could stand there all day and float around. Mr. Reagle grew up on a lake, and I used to paint people's docks. So sometimes I'd be out like chest deep in water, with a paintbrush up over my head, painting the dock, and there'd be bugs and spiders and stuff like this crawling all over the place on the water. If a drip of paint or stain would fall in the water, one of the things that happens with water with detergents is that it destroys this surface tension. The molecules don't have the connection to each other anymore, and the surface tension just immediately goes away. So there'd be all these bugs going around, and if a drip came off the paintbrush and hit the water, they would all just sink. I wonder what they were thinking. They're like, why aren't we standing on the water anymore? So it's also why when you jump into water, you don't want that water to be perfectly smooth, because then you have to break through the surface tension, and that tends to hurt a little bit. It's like landing on concrete. It's why people break their legs when they jump off of bridges into the river. You're actually breaking your leg on landing on the water, not going down and hitting the ground. So also in liquids, another vocab term that you have to know is viscosity. And viscosity is a property of a liquid and its resistance to flowing. So you can think of like Heinz ketchup, where you tilt that bottle and the ketchup just doesn't want to pour out and you need to encourage it a lot. That means Heinz ketchup has a high viscosity. So things with a high viscosity flow slow. Well, the reason different liquids have different viscosities has to do with the shapes of the molecules that make them up. If you have a molecule that's really big, it's not going to flow as quickly. If you have a molecule that has lots of branches coming off of it, those branches can actually get caught and tangled on other molecule branches, and it's not going to flow as quickly. There's a whole science behind viscosity, especially if you work in like the oil industry. Specifically, like if you were creating different oils for cars and things like that, you have to really be able to control the viscosity. So here, speaking of oil, we have motor oil of different viscosities, and we have test tubes of it, and we dropped a ball bearing into each. You can see in this one the ball bearing sank the fastest, and in this one it's going really slow as it sinks. That means this fluid has the highest resistance to flowing, and this one would have the highest viscosity. Over here we have 5 test tubes. They've all been tilted. You can see these ones are pouring out more like the kind of liquid that you would be used to. These ones are also liquids, but they're more like gels, and they just have really high viscosity and they're not flowing out. So the third state of matter that you're used to is called a gas. And for the first time, a gas is a state of matter that has open space between the molecules. So you can have a molecule that's not in contact with any of the other molecules in that gas. And as a result, gases have no definite shape and no definite volume. So a solid has a definite shape and a definite volume. A liquid has a definite volume, but no definite shape, and gases don't have either. One thing you might find interesting and didn't realize is that a gas is also considered a fluid. Remember, fluid doesn't just mean a liquid. A fluid means anything that can flow, anything that can have the molecules slide over each other. And a gas definitely fits that bill as well. Gases can move around in pretty much any way they want. So the gas's volume will take up whatever container you put it in, and its shape will take up whatever container that you put it in. The fourth state of matter we're going to discuss, like there are 5, but the fourth state of matter we're going to discuss is called plasma. And plasma is sort of like a gas. It kind of starts as a gas that then gets super duper energized. And so energized that the electrons that would normally be orbiting the individual atoms and molecules in the gas are stripped off and are now kind of flying around wherever they want to in the gas. This takes a lot of energy to make this happen. So much energy that this is what stars are made of. So since stars make up most of the mass in the universe, I mean, if you think about our sun is more massive than all of the other planets and comets and meteors and asteroids in our solar system combined. Most of the mass in all of the universe is found in stars. This means that plasma is the most common form of matter in the universe. So it's not the solid liquid gas that we're used to seeing all the time, but in fact plasma is the most common form of matter in the universe. Now, since these electrons are flying around and can move around, plasma can also conduct electricity really well and can create even its own electrical currents. So I have a video here to watch. It's one of those Veritasium videos, and this is the second time I'm recording this note video because the last time I didn't realize that the iPad fell asleep while the video was on and I had to start all over. So see if I can prevent that from happening this time. So these guys are these are a couple of physicists. This is the kind of thing that you do when you're a physicist and apparently you're bored. They're going to test a theory that you can make plasma in a microwave. I would not try this at home because I would really, if I were you, I wouldn't want to damage your parents' microwave.
So today I'm at the University of Sydney with Steve Bose, and we are exploring everyone's favorite state of matter, plasma.
No, actually, my favourite state of matter is the BoseEinstein Condensate, but that's just me.
That's for another episode. So for now, we are trying to replicate these videos that you can see on the web where people use a simple grape and a microwave to produce plasma.
We took a grape and cut it part of the way through so you'd have 2 halves with a tiny little isthmus of the grape skin holding the 2 halves together. Put that in the microwave oven now. Try to pop that up so it's sitting in the middle.
All set.
Is this going to be dangerous?
I don't think so, but we are experts, so be careful if you're trying this at home.
And bingo.
Where's the plasma? Whoa! There's the plasma.
Holy. Hey!
Wow, well that was some pretty amazing plasma that we made in this microwave. What is plasma for people who don't know?
Okay, if you take a gas and you put lots of energy into it till it gets very hot and the particles are very, very energetic, you start to rip electrons off the molecules. So you end up with a soup made up of negatively charged electrons mixed in but moving freely with a bunch of positively charged air molecules.
And why does that give off light?
Well, any time that you put energy into atoms and molecules, the electrons start moving around, changing orbits and that kind of stuff. So anytime the electrons are being excited and de-excited, you're going to get light. Whoa! Who needs drugs?
And we also imagine that it's very hot, so it would be glowing white hot anyway.
Yeah, possibly also some of the ingredients in that plasma have actually been heated up very high, so they're incandescent. They just glow because they're hot.
Okay.
Don't know.
So what did we find worked the best with microwaving our grape? What lessons did we learn?
Okay, first thing we discovered was we got better results if we dried the grape up before we put it in. We found too much water, gave off too much steam, and they tend to extinguish the plasma.
And then Steve came up with a great idea of actually cutting the grape completely in half, but using these dangling flaps of grape skin.
And grafting them together, just laying them over the top of each other.
And that seemed to work better because we could reduce the volume of the grape, and that seemed to help.
Yeah, but because we used smaller pieces of grape, so we had less steam, also less thermal mass, and possibly less grape absorbing less microwave energy, so we got higher fields.
Oh,
Holy feces. Yes, did you see that fireball? That was an example of multiple plasma.
And then, of course, the trick was to try to capture the plasma so that we didn't do damage to the microwave, for one thing. And second of all, so that we could observe it quite nicely in a container. But we had trouble with the glass that we were using, a few glasses. We couldn't seem to get it to work.
The guess is that the glass was absorbing too much of the microwave energy, and so we weren't getting the very high fields you need to make the plasma. Oh, yeah. Oh, no.
So we moved over to a plastic container, which seemed to do much better.
Yeah, if you can just tolerate the fact that the plastic container melted afterwards. Plastic container to capture the action and adventures. Look. Go the laws of physics.
Yeah.
Oh, yeah, it's still going. Go the laws of physics.
Yeah.
Oh, yeah. It's still going.
Do you smell that? Is that a new smell? Is that a melting plastic?
Are you still filming?
Oh my! Hang on.
Catch that! Look, it's got a smile. Even the container's got a smiley face after that run.
Yeah, it was only like a one-hit gig. So, what sort of future investigations would you like to do here?
Okay, now, in order to understand exactly why this happens, we really need to be able to control the variables inside that grape. Okay, we can't control the ingredients of a grape; they come to us as is. So what we'd like to do is make an artificial grape. So get cotton balls. We can put conductive liquid in it. We could put salty water in it. We can put grape juice and control the volume of these things. So one by one we can actually nail down the different variables. And we'll have to find some artificial skin to replace the grape skin. I don't know if it has to be grape skin. Maybe a wet piece of paper might do the job. I don't know.
Okay, so you should look forward to that on another episode of Veritasium. Care for a grape?
Thank you very much.
Physics is tasty.
Holy! Oh, see, what did I tell you? What did I tell you? Oh! But wait, there's more.
All right, managed to get that video in without the iPad falling asleep this time. So that was just showing you what some plasma looks like. So they were using the microwaves in the microwave oven that we discussed in class to super excite the gas that was in there. And as you saw, they don't really know why it does what it does. And he talked about how you would have to do an experiment to figure it out and how you'd have to control all of those variables. So it's a lot of things that we talk about. All right, so, and you also heard him mention the fifth state of matter, the BoseEinstein Condensate. So the solid liquid gas that you're familiar with, you can kind of think of plasma as being beyond the gas. Well, the BoseEinstein Condensate is on the other side. It's kind of like an even more compressed solid, if you can think of it of plasma as being like an even more energized gas. All right, so what do you call it when you move from one state of matter to another? A lot of these words you're going to be familiar with, but a couple of them you might not be. One is melting, and melting is what we call it when you go from a solid to a liquid. So most substances have specific melting points, and you can even use the melting points to identify the substances in some cases. So this is the temperature at which the solid turns into the liquid. And it happens, I want you to think about all of these in terms of thermal energy. So what happens is in a solid you have the molecules like in that like rigid kind of structure, they're attached to each other, they're holding that shape, and they start to vibrate faster and faster and faster. And as you add thermal energy, they start going faster and faster and faster, and eventually they reach a vibration point, a speed point, where they break the bonds that are holding each other together. Now, I don't mean the chemical bonds. They're not changing what chemical they are, but they're breaking that like attraction that they have to their neighbor. And this allows them to kind of start to roll around and roll across the surfaces. And that's what you see when you see things start to melt. Now, what's kind of interesting with the way that this works is that materials will stay the same temperature until the entire thing is melted. So if I have water and I put it in the freezer and I set the freezer to like negative 15 degrees Celsius, and I put a thermometer in that water will start to freeze and start to freeze and start to freeze and start to freeze. But in like that whole freezing process until all of the liquid is turned into a solid, it will stop and stay at 0 degrees Celsius, which is the freezing point. And then once it's all frozen into a solid, then it can actually start to get cold again. And the same thing goes whenever it does the reverse and melts, which is, I guess, what we're talking about here, is that melting water will stay at 0 degrees Celsius until it's all melted into the liquid form, and then the liquid can start to get warmer. And the same thing happens at boiling as well. So freezing is the opposite of melting. Things have their freezing point. This is the point at which they turn from the solid or the liquid into the solid. And this happens, it's the opposite of how things melt. The atoms and molecules start to vibrate slower and slower and slower and start to line up and kind of form hand-holding connections with the molecules next to them and kind of link up in those lattice structures. So what's interesting is that the act of freezing, the act of turning from the liquid into the solid, gives off thermal energy. And this is for reasons that you'll talk a lot more about at the high school, things called entropy and enthalpy, but those aren't things we're going to get into in 8th grade. So if it's really cold out, you can throw things like a bucket of water up in the air, and it will actually freeze right in the air, and then it comes crashing down. So this was a picture that was taken just at the right time. But people have always talked about, that would be interesting if you could do that. Well, there are places that it gets cold enough that you can do that. Vaporization is what you call it when you go from the liquid to the gas. So you might think of this as evaporation, but that's a special thing we're going to talk about in a second. The actual change of state is called vaporization. And this happens when you have the liquid where the particles can slide over each other, and now you've added more and more and more and more energy, and it's gotten to the point where the particles don't need to be touching the other molecules anymore, and they get some space between them. And as soon as you develop some space between the molecules, you're no longer a liquid, you're a gas. So the two kinds of vaporization are evaporation and boiling. And the difference between the two is where they take place. Evaporation always happens at the surface of the liquid. Things don't evaporate from the bottom of the lake. They evaporate from the surface. The water evaporates from the surface of the water. And evaporation often has a lot to do with like difference in humidity between, like if it's low humidity in a room, the water will evaporate faster. Boiling happens whenever you get vaporization that's occurring below the surface of the water. It can also happen at the surface of the water, just like evaporation. But if you have liquids turning into gases below the surface of the water, you suddenly get a bubble that forms, which is the gaseous version of that material, and then it floats to the top. And something that students often struggle with a little bit, let me throw a picture up here, because I ask this question sometimes and people don't know how to answer it. So let's say I had a beaker, and I have filled it with water. And I've put it on a hot plate, and it's getting really, really, really warm. So it's sitting on a hot plate, and it's getting warm and warm and warm. And suddenly, we get a bubble that forms in here, and we get another bubble that forms in here, another bubble that forms in here, and these bubbles start to float towards the surface. Well, if I could kind of like stop time, if I could somehow, or just be fast enough that I could take a sample of that bubble right there, what kind of gas would I find in that bubble? When I ask students this, oftentimes I get answers that are the same gases that we breathe in. People will say things like hydrogen gas and oxygen gas and carbon dioxide gas. But think about it. All that was here was water. So the only gas that's in this bubble is water. It's water vapor. So those bubbles that you see when water is boiling, that is 100% water vapor that's in that bubble. That is the gaseous state of water that you're seeing. So vaporization, the actual temperature that things boil at, changes and has a lot to do with pressure. The more that the air is pushing down on the surface, the more energy that you have to put into the molecules before they can break away and go into the air and vaporize. So if you are in a place with really high pressure and you're trying to boil water, that water is going to reach a higher temperature than normal. Likewise, on the flip side, if you're in a place with low pressure, you can boil water at a lower temperature. So if you were hiking up in the mountains, water would actually boil more at like 95 degrees Celsius instead of 100 degrees Celsius. Now, don't think that that's going to make it so that you can cook food faster, because since the water is actually a cooler temperature, it takes longer to cook the foods. It's something that if you see on recipes sometimes, there'll be different temperature settings and different time settings based on high altitude cooking, if you lived in a place that was in the mountains. So vaporization ends up absorbing energy. So vaporization pulls energy in when it happens. If you remember, freezing gives energy off, but vaporization pulls energy in. And this is what your body utilizes when you sweat. So the reason that you sweat is to cool you off. If you're hot and your body is overheated and your body is at a higher temperature than it would like to be, your body will secrete a liquid out onto your skin. That liquid will vaporize. It will evaporate off into the air around, and it will take with it a lot of the thermal energy that's in your body, because it has to absorb energy in order to make that happen. So it's going to absorb the thermal energy, it's going to absorb the heat out of your body and then release it into the air. It's very, very effective. Condensation is what you call it when something turns from a gas into a liquid. So this is how, like the fog builds up on the mirror when you're taking a shower and that kind of stuff. So this happens when you have those gas particles with all the space in between them, and they start to slow down and they start to move at a slower speed, and they start to come in contact with each other and start touching each other and kind of sticking to each other a little bit. So one thing to note is that water vapor is invisible. You cannot see water vapor. You can see liquid water, you can see solid water, but you can't see water vapor. Things like fog and stuff like that you see, that's not water vapor, that's actually liquid water. They're really super tiny, microscopic almost droplets of water that are stuck to things like dust particles in the air. So when you see like fog, or you see your breath when it's a chilly day, that's actually liquid water, that's not gaseous water. All right, here's a couple that you might not be familiar with. The first is called sublimation. There are some materials that will go right from a solid into a gas, which means there's no liquid state. You're skipping the liquid state altogether. Two things that you might be familiar with that do this are things like dry ice, which is just the solid form of carbon dioxide. If you breathe out and catch your breath in like a balloon and get it so cold that gas would actually turn into a solid, you would have dry ice. People often use dry ice when they're going on long trips and they want to pack food and keep it really cold, because dry ice has a really cold temperature. It's something around the range of like negative 40 degrees Celsius. I'm really not sure. I'm just kind of making that up, but I think it's somewhere around there. So it's cold, and then when it melts, it doesn't turn into liquid. So you don't have to worry about lugging around, like water. Like the coolers get really heavy when they fill up with liquid at the bottom. Dry ice turns right into a gas. Mothballs are another good example of things that sublime. You might, depends on how old your grandparents are, but like my grandparents, when you went into the house, if you opened up a closet or something, you would smell mothballs. Because they would actually get these things and they would just kind of throw them in the back corners of closets. They would kind of spread them around because they give off a gas. The chemical itself is called naphthalene. Well, bugs and things like little rodents hate the smell of it, so they stay away. So the grandparents would like throw these things around, and then they wouldn't have to worry about pests in the house, especially around the wintertime. But you can smell it when you walk in. It's not a very fun odor. Some people do the same thing with those it's like monkey balls, those Osage oranges that you see growing around Shaler. They drop them off, they pick them up, and they kind of leave them around in the corners of their houses. There is a volatile chemical in the rind that kind of goes into the air, and bugs hate it, so it works the exact same way. Just in that case, it's a liquid, so it's not really sublimation. So one thing about sublimation, remember, it's going from the solid right to the gas. So these things will actually disappear. If you watch them, they just disappear into nothing. They disappear into gas. Their volume and their mass gets smaller and smaller and smaller and smaller until there's nothing left that you can see. The opposite of sublimation is called deposition. And deposition is whenever a material turns from a gas directly into a solid, completely skipping the liquid state again. So this is actually how snow forms, interestingly enough. When snow forms, those snow crystals are forming right out of water vapor in the air. It is water vapor that is turning directly into ice. It's skipping the liquid phase. If it would go through the liquid phase, if it would have a chance to melt or condense into liquid before it would freeze, you don't get snow. In those cases, you get hail. You would get little balls of ice instead of really pretty crystals. So snow develops through the process of deposition, not the process of freezing, which most people think. And this is an exothermic change of state. It gives off energy, just like the freezing gave off energy, and energy was given off whenever it went from a liquid to a solid. This is going from a gas to a solid, so it actually gives off even more energy. There's a bigger energy output from this process. And this is why, if you've ever noticed, if you're out playing in the wintertime, that when it starts to snow, it actually feels a little bit warmer out, because it actually will give a little bit of enough thermal energy to the air to kind of raise the temperature a degree. So there is a very special temperature. We're not going to really do anything with it in class, but you should know about it, and you'll use it a lot at the high school. And it's called the triple point. And it's a really interesting temperature with a really interesting phenomena. It's the exact temperature. There's also some pressure involved as well. It's the exact temperature where a liquid will be a solid, a liquid, or I should say an object or a form of matter will be a solid, a liquid, and a gas at the same time. And for water, the temperature is 0.01 degrees Celsius, which is equal to these two temperatures here in those other two scales. But at that temperature, you could have like a glass of water, for example, and it would have ice in it, and there would be water vapor. So you would have all three states of matter in one glass of water. There's an interesting Aura video that shows a triple point of a different kind of liquid or material. So there's two quick check questions that you are going to be answering questions about here on this page using this chart that we're going to look at. So the stuff on the chart, you'll see that the triple point is listed on there, but you'll also see that there's this thing called the critical point. And the critical point happens at really extreme kind of temperature and pressure combinations where it's impossible to tell the difference between a liquid and a gas. Typically this would happen at really low pressure, so gases would just like, or I'm sorry, liquids would just like bubble right into gases. Nothing's there to be able to force them together to form into liquids. This is not a big deal. There are no questions about critical point on the quizzes. It's just to help you read this chart a little bit better. So here is the chart. So it looks super complicated. Anytime you see something that looks really complicated, they like to give you really complicated looking charts on the Science PSSA. Break it down. So let's check out each of the sides. So over here we have pressure. So these are all pressure measurements, and these are in units called pascals. And you should be able to recognize the prefixes on here. So this would be 1 Pascal down here, 10, and then 100, 1 kilopascal, 1 megapascal, 1 gigapascal, and 1 terapascal. The prefixes in the SI system are just the same as for computers. That's why computers use those. Down here at the bottom we have temperature in degrees Celsius. At the top we have temperature in degrees Kelvin. So the top and bottom are both temperature. Over here we also have pressure, but it's pressure measured in bars instead of pascals. So you're really just looking at a chart here, a graph that is comparing temperature and pressure. And based on where you're at, once you get the temperature and the pressure, then it'll tell you what state of matter you would be in. So if we were looking at the freezing point of water, for example, that would be at 0 degrees Celsius. It says that this is at 1 atmosphere, so the pressure, if you were at the beach, the amount of air pressure that you would experience here is apparently 100 kilopascals. So that's why we have 0 degrees Celsius being the freezing point. If you go colder than that, well, it becomes a solid. We get in the solid range. If you're warmer than that, you're in the liquid range. If you get up to 100 degrees Celsius, now you're boiling, and you go warmer, now you're in the vapor stage. So you can look up any combination of pressure. So pressure going up, temperature going up, and seeing what happens with the material. So do your best, try to figure out where or what state of matter each of those quick check questions falls into. Thanks for sticking around. I'll see you in class.